So the first section, which I believe is in the A3 appendix of your book, is a little review of complex numbers.
Is that A3?
A3, yeah.
What's the section called?
Appendix.
Yeah, I mean, it's just, the whole theme is about complex numbers.
Oh, section.
Yeah, sure.
So is the plural appendix?
So the basic idea is that any complex number, which we're going to call z, can be written as a plus bi. Okay? If you see the notation z with a bar on top, that refers to the complex conjugate, which simply means to take the imaginary portion of this complex number and do the opposite. So instead of a plus bi, you would have a minus bi. Okay? So what is the conjugate of 2 plus 5i? 2 minus 5i. What's the conjugate of 6i? What's the conjugate of 4? This is just 4 because there's no imaginary portion with that. Does that make sense? Okay. You probably remember this definition that I is equal to the square root of -1. Okay, that's our definition for the imaginary number system. And with that, you should be able to compute several powers of I. So we'll go through the first cycle, and then I'll show you what I think is the easiest way to work with large powers. This is just going to be -1, because when you square, all it does is cancel the root, right? I cubed is the same as I times I squared. And what's I squared? -1. So this is just -I.
So is that the same thing as just like square root of 1?
Well, this would be the same. We wouldn't write it this way, but it's the same as this. Okay, so, and we really don't write square root of -1 either. We just use that as the definition. So most of your answers are, basically all your answers with complex numbers are going to have I or some version of it. Okay? What's I to the 4? What does that equal? How can we split this up? Do we know what I squared equals? Times is
1.
Now, if I go one further, I think you'll see the idea. I to the 5th, we can do several options. Why don't I just do I to the 4 times I? And what's I to the 4? I to the 4 is just 1. Oh, I see. So the answer is just I. Is that what you were saying? Okay. And you'll notice the pattern. Yeah, it just repeats. I, -1, -I, 1. And then, well, every 4. And then and it goes I, -1, -I, 1. And it just keeps repeating. Okay?
Let's call that a period.
So then, for large powers, here's what I suggest. Let's say I have I to the 54. Okay? You could try to think of the pattern, or period as John called it, and figure out where it falls within the cycle. Okay? I think the easiest thing to do is to always refer back to this, because really all you need to know is that I squared is equal to -1, And you can use that for any problem.
So this equals 1, right?
I don't know. Let's see.
I bet you it does. Is the last number?
Here's what I would do. Figure out how many times 2 goes into 54. That's not hard, right? What is it? 27. Good. So then we know what I squared is. That's just -1. But we still have what power left? And now what's -1 to an odd power? -1. Yes.
I mean, that's pretty easy, but are we going to have a calculator if we want to?
Not necessarily. Okay, in fact, I think this entire unit is strictly no calculator. Okay. You guys kind of understand how that works? Okay. Let's try one more. I to the 947. I always, again, think about I squared first. See how many of those you can fit into 947.
You can't fit any. Let's do 3.
How many, John? 3?
Yep.
Not quite.
5.
Well, go by 946 and have one left over.
So, yeah, 2 goes into 946 evenly with 1 left over. I agree. What would that be?
Nothing good. What do you want me to do? 473 times.
473?
Yep.
That gets us to 946, right?
Yes.
But we still have an extra I because we need to make this equal 947. Does that make sense?
You just say like I squared to an odd power is -1 and then multiply by another I.
So that answer is going to be what?
1.
Not 1. A -1 to an odd is negative, so it's negative I.
Oh my God.
Don't overcomplicate it. Are we confused or are we okay?
I'm confused by what they're saying.
What are you confused, John?
How'd you get -5?
Because -1 to the 473 is -1. -1 times I, it's just negative I.
So since there's
Yes.
Go ahead, Colleen. What is it? Since there is...
okay, so okay, okay.
Are you sure?
Yeah, I was gonna say okay.
Would anyone else benefit from your comment, possibly?
These people didn't listen. Okay, so the extra I came because there was one extra because you did from the 946.
Yes.
And then you did like the 2 times that outside number.
Yes.
And the extra I is just chilling up there.
Yes.
Okay.
Because these, when you split this up using the I squared technique, we have to have a total of 947. So right here, these give me 946. If this is a power of 1, now there's a total of 947. Okay?
Alright, Mr. G, I get it from when you have I squared and it gives you -1. So then the next step I have is -1 to the 473 times I.
Yep.
But then how does the -1 turn into, like I thought, don't you have the times by 473 again?
What does the 473 exponent mean?
You tell me, multiply it by something.
You multiply... Really? At this level?
Oh, never mind, I get it.
You tell me. Are you sure, John? You got it?
Yeah.
Okay.
I got it.
Now, with this section, you should be able to add, subtract, multiply, and divide complex numbers. So we'll do a quick example of each. Let's say you have 5 minus 4i times 2 plus 4i. my advice is to do what you think you should do, and then if you see any I squareds, use the definition, which is -1, to figure it out. So what do you think you should do here? Sure. So we get 10 plus 20i minus 8i minus 16i squared. We can combine some things. 20i minus 8i is 12i. Minus 16, what's I squared? -1. So I really have 10 and then add 16. That's 26 plus 12i is your final answer.
So it's like X.
Yeah, you treat it as a variable, but then since you know that I squared is -1, you go ahead and plug it in and then simplify. That's a good point. Yes?
So you never want to substitute in a root -1
No.
for I, because that's not.
I mean, we just know that that's what that means. Yeah. And a good side note to write here is that all answers will be written in A plus BI form. So even though we have all these complex numbers doing stuff to each other, adding, subtracting, multiplying, it always boils down to a real number plus an imaginary portion. Does that make sense? Okay. So we're always going to have that format. Let's see. And you guys have done this before. This part's review. I hope you guys aren't completely confused because, yeah, this is from Algebra 2. Yeah. I don't think we did anything with imaginary stuff in the beginning. Okay. So here we have a complex number divided by a complex number. Does anybody remember what the technique was here? Yes.
Conjugate.
Yes, very good. Multiply top and bottom by the conjugate of the denominator. So anytime you have division, take the denominator, use the conjugate, multiply it to the top and to the bottom. And go ahead.
Like anytime you multiply by a conjugate, the real number disappears.
Yes, that's the whole point. The middle terms, which will have the i's, like up here, these i's would go away because they're going to be identical but opposite. Okay, so let's see. On top, what do we get? We get 2 minus 4i minus 4i plus, good. The denominator, 1, let's not skip that, but you're right. And I'll only do this once. Minus 2i plus 2i, right? Minus 4i squared. These are always going to cancel when you're doing conjugates, so you don't have to do that step. And now, what is I squared equal to? So let's clean everything up as much as possible. In the numerator, this 2, what do I do with it? What do I combine with the 2? 2 and -8. Very good. So that's -6 minus 8i over 5. 1 plus 4 is 5. So now we're always going to write our answers in A plus BI form. So all we do is just divide everything. -6 over 5, that's your real portion, minus 8 over 5 times I. So again, everything can be written in this format. Real number plus the imaginary stuff, or minus.
Wait, how did we jump from the second to...
From here to here?
Oh, you just put it.
Yeah, you got it?
No
Okay.
questions, no questions. You want to put it in
Yes.
equals.
How'd you go from 1 minus 4i squared to 5?
because I squared is equal to negative 1, so negative times negative is positive 4. Does that make sense? And then you combine it to get 5. Anything else? Okay. Well, we still have a few. So that's adding, subtracting, multiplying, dividing. I think we're pretty good there. Let's go add. I don't think this is in the book, so just kind of make sure you take good notes on this.
So was that example multiplication what you said?
Well, this included everything. This was multiplying, but within we had to add and subtract, didn't we? And then here we had division, but we also had to multiply, and we added and subtracted. So, I mean, these two cover everything. If you ever see this, absolute value of 5 minus 12i, or really anything like this with complex numbers, the way to think about this is that it's the distance. What's absolute value mean? Distance to 0. Okay, the problem is here we have two things. We have a real and an imaginary thing. So instead of saying distance to 0, we're going to say distance to origin. Because we're going to think of this as like a x and a y. Like if you graphed and you thought of this as the real axis and this as the imaginary axis, you can map this or plot the location of this number. And this is what we call the complex plane. Yeah, you should write this down. So if I asked you, for the time being, just look at what's inside, what's the real portion of it, what would you say? So you go out 5 units in the real direction. Okay? What's the imaginary part? Negative 12. So we're going to go down negative 12. This is the imaginary axis. So then this point gets mapped out or plotted to this location. Sorry, that's a really big point. Sorry about that. Now, if I want to find the distance to the origin, I just want to find out this. Can I do that pretty easily?
Yeah.
How? You tell me. You could use distance formula. Pythagorean theorem will do the trick, right? If you make a triangle here.
Is it a 5, 12, 13 or no?
Yeah. It's
Wow.
5, 12. What's the hypotenuse? So the answer to this is 13.
That's it?
That's it.
That's the answer?
It's just, whenever you see this, it just wants you to tell how far away it is from the origin on a complex plane like this. There's a shortcut that you guys can learn. This was a nice Pythagorean triple, so you didn't really have to do too much work. But if you didn't know that the hypotenuse was 12, or I'm sorry, that the hypotenuse was 13, you would do 5 squared, 12 squared, add it up and square root it, right? So what would the shortcut be for this? Almost. The square root of that, right. So this is like your formula if you want to write it down. Okay? Any questions on how this works? Okay. Trying to review everything about complex numbers.
You always have to take the positive number, right?
Yes.
Negative 5 minus negative 12i, 5, 12.
Well, when you square it, it wouldn't make a difference, right?
Yeah.
So, either way.
Jim has a question.
You sure?
Are we ever gonna? We're always gonna define distance to the origin?
Yes. That's the definition of absolute value. That's what it means. With just one normal number, it's distance to 0 on a number line. When you have a complex number with two terms, instead of 0, you think of 0 as the origin. So it's the same idea. Okay. What if I have 5 plus 7i equals 3a minus 9bi, and I ask you to solve for a and b? Any ideas?
Just make it 3a equal 5, 9 7.
So why does 3a have to equal 5?
Because it says equal.
Looking for a little deeper, but yeah.
So it's kind of like
That's a non-imaginary.
That's the non-imaginary number on each side. And since they have to equal each other, 5 has to equal 3a. And what else has to equal? 7 has to equal negative 9b. Does that make sense? On the left we have 5 for the real. On the right we have 3a for the real. So you set them equal. On the left we have 7 for imaginary, negative 9b for imaginary. So you just set them equal. So a is 5 over 3.
Wait, why do you move it out?
Well, because it would end up canceling out anyway. Like if you wrote it in, right?
Where's G?
What's B? Yep. What's up, John?
Is there gonna be a problem where there's like a triangle?
Yeah, sure. I'm getting there. We're doing about 2 weeks worth of advanced algebra in about 25 minutes here. So this is what? Okay. Simplifying radicals that have negatives in the radical. This is the same as, yeah, I won't skip that step quite yet, but you guys agree that it's the same as root 90 times negative 1 plus 5 times root 40 times negative 1?
Did you say plus I?
That's the whole point, yeah. So this is just I, and if you know how to reduce root 90, what is it? 3 root 10? Plus 5, what's root 40?
2.
So we have 3 root 10 plus 10 root 10. That's 13 root 10. And since they are both imaginary, we can combine them to make 13 root 10 times I. Easy, right?
Yep.
Do we need more examples of roots?
Nope.
Okay. Here's your trinomial. Go ahead and try this one on your own real quick. Several.
So I should start a new page.
Yes. Anybody know when this period is over? With the new...
So if they go after third, do they add on to
When the
it?
bell rings.
That's my answer.
Around 45-ish, right?
Yeah, that sounds
Five,
right.
So if we
42.
started-
42?
I bet.
Isn't that when we normally end?
No, we end at 44 usually. We get out
No,
39.
we end at 43.
42 or 43 is when we normally end. It's going to be later than that.
It's going to be like 45.
Yeah.
It's like a class period.
Okay.
45.
45.
Yeah.
Let's just say 42.
Because it's
for sure.
after third, so we add it on.
Why is everyone yelling?
We can discuss this, guys.
How about you do this real quick, and I'll go find out for sure.
Alright.
Because I know
Why
where
don't we just
this
wait till
guy.
the first bell rings?
Are you
Can
trying?
I add on number
Are you making me? Are you
Yeah.
trying?
So you're just, okay. I don't really understand. I don't get how there's eyes in it. It's really, oh,
Yeah.
yeah, your head's in there.
The only problem is, like, why would we all of a sudden go from imaginary to just, like,
Because that's gonna have the imaginary. So smart. Thanks,
Sorry.
Sabrina.
Okay, it's 48.
I was closer to that one.
Because period 3 is going to be 44 minutes plus the 10 minutes of reading plus the 5 minutes of announcements. So period 3 is the long period for the day.
You want done?
Yeah.
I read on my own.
You done, John?
Yeah. Wait, give you my answer?
Walk me through.
Alright. So you throw quadratic formulas.
Yep.
Same way you do it. No. No.
Go ahead.
I'm a confused student. I don't know what that means.
Alright, 4 plus or minus.
Uh-huh.
And then put the square root of 16 minus 24. 4 times 1 times 6.
Oh, I see. Uh-huh.
Will be 2a, which is 2.
Gotcha.
The number for the x squared.
Mm-hmm.
And solve it all out like you would.
Solve it all out.
Yep. So you get -8 under the root of 2. And then take out an I out of the 8. So it's root 8 times I.
And don't we know what root 8 is, though?
2 root 2. Over 2 and then simplify and then that's your answer.
How do I simplify that?
Divide everything by 2.
So 2
Plus or minus root 2 I.
questions.
And
Turkey's a ham?
turkey.
Turkey is a ham.
That doesn't make any
Hey,
sense.
don't even worry about what I say, alright? Just let me.
Remember that, guys. Don't ever worry about what I say.
Never worry about
Yes, Sabrina.
Does it matter if the I goes in front of the root, or does it have to go?
So if you wrote it like that,
Yeah.
it's the same. Yeah. Good question.
Did you get that?
All right. Next section. 13.1. Division of polynomials. This will be a quick review. If you guys settle down, we'll be done in about 5-6 minutes here.
Wait, so the last thing wasn't
Why are you
13?
stressing me?
That was like a
It was the necessary knowledge before we started the unit.
Wait, that wasn't.
I said it was Appendix 3, right?
I don't know what appendix means. All I know
Google
is
it.
I have
It's an
one.
organic body.
All I know is that I have
It's in your body.
Ah,
It might explode.
Okay.
I want to know what I got on the quiz.
I can show you your scores if there's time. The plan, I wrote it on the board, right?
Okay.
What does it say for Monday? Go over quiz,
Review 11, 12.
review. So then your test is going to be on Tuesday.
What was chapter 11?
11 was systems.
What was chapter?
Okay. Division of polynomials. We have the division algorithm, which says that any polynomial, so this is just any polynomial, when you're dividing it by something, can always be written as the divisor. So this is what you're dividing by. Times the quotient plus a remainder.
Mr. Gonzalez?
Yeah.
Use the wrong form of yours. It's killing me.
Oh, that's a big, yep.
Thank you.
Drives me nuts too. Thank-
You shouldn't have changed it
Why?
because it was killing her.
Well, it kills me too. I don't like doing that.
Is that a Q or a G?
Q, quotient,
Oh.
not quote. Quote.
Look at it.
I can't even say it.
It looks like a G.
How?
Oh, it doesn't? It goes the opposite way of a G.
Yeah.
Oh, I don't know.
Anyway, this represents a remainder.
Whoa, I didn't know.
Should study that.
So first I will illustrate this idea with a baby example. Let's say we are dividing 27 by 4. 4 goes into 27.
Really? I'm just kidding.
6 times.
6 times. Subtract 24. What's the remainder? So according to the division algorithm, what's up, Jim?
No. Dude, everyone just makes their little comments and just like, oh my god. That was.
Imagine how I feel.
I'm sorry.
Dude, give me with that smile.
You see how I'm saying? It's classic, yo. Oh, he's just.
Okay, 27. What's the divisor? What's the quotient? 6. What's the remainder? This is all it says.
Wait, why'd you put 4?
I'm just following the pattern here. I'd like to show you your quizzes, but
Wait,
I don't want to see what it is.
polynomial just means like 3x squared plus 6x. It's just one of those expressions. I said I'm doing a little baby example to illustrate the idea. Right. Well, technically it is. It just doesn't have any variables.
When you said a baby example, she asked if it was a real baby. I'm just gonna let you know this. Is it a real?
Oh my gosh, this class is going to be the death of me.
Why do you think I said that?
Quiz time.
Among other things. Okay, so now here's the real deal. Let's say we have a polynomial, x cubed plus 2x squared minus 4, and we're dividing it by x minus 3.
This class.
You know there's an R after Mr., right?
It's the G.
Oh, it's the G.
Let's divide. You guys remember this, right?
Yeah.
X cubed
No. Is it squared? Isn't it supposed to be squared?
plus 2x squared. What do we need after this?
Plus 0.
Good. Minus 4. You can either do long division,
The zero.
synthetic.
Let's do both.
You can do long, which I'm going to skip,
The other one's better when you just put the 3 in there.
or synthetic. Most people remember how to do long division. Synthetic is kind of easy to forget, but also easy to review.
Upside down the columns and
You set this equal to 0. What do you get?
4.
3. Block D is going to be watching this video today because I'm not going to be there.
Like during class?
Yeah.
Boy John.
Hey!
It's your boy John.
Hi, Alex.
Oh my gosh. What do I write down here? Thanks, John. 1, 2, 0, negative 4. Not you, John Alex.
Oh.
Do you guys remember the steps? Bring down the 1 is the first step.
3 times that, right?
Write it down. And then all you do is multiply this number with the number in the little box. And then you keep adding and repeat. So what's 1 times 3? Add it up. And now repeat. Add or multiply 3 and 5. 15. John, go in the hall.
I'm sorry, Mr. G.
No, go in the hall. That's why you're going in the hall. Let's go. Go ahead.
Really?
Everybody see where we got these numbers from? Okay. So this means x squared plus 5x plus 15. This 41 is your remainder. I'll talk to you when the class is over. So now, here's your quotient. Whoops. Here's your remainder. We already got that. This up here was your divisor, right? And this was your original polynomial. So according to the division algorithm, I can take original polynomial, which is x cubed plus 2x squared minus 4, and how do I write it?
X minus 3
Divisor, which is x minus 3, times
times x squared plus 5x plus 15.
x squared plus 5x plus 15, your quotient, plus
41.
remainder, 41. Okay? Yes?
Wait, what is the imaginary numbers of
Well, eventually we're going to start solving higher order equations, not just quadratics like cubics, quartics, and stuff, and they're going to have frequently imaginary answers. So that's where this is headed. Yes?
Why are we doing this? It's going to help us out when we have imaginary numbers?
Yes? Absolutely.
Imaginary numbers are used in that way.
Usually in circuits with electricity and magnetism.
Haven't got that far into
So
this.
is that
Right. I mean, that's where they start. They indicate different flow and direction.
Is that what leave our answer?
Yeah, they'll ask you to put it in this form.
Oh.
Yep. All right. Farewell.